So welcome back, everybody. We're now in the 6th week of class. As usual, we have a new homework assignment. It's up on the board, also on Canvas. Make sure you get the worksheet for that at the front of the room and also turn in your assignment from last week. Also just want to remind you that the first test is a week away. So next Tuesday, when you turn in homework 6, will be the day of the test. We'll do that in lecture. Related to that, in lab this week, we're not going to be doing an experiment like we usually do. Instead, we're going to go through the review problems to help you prepare for the first test. All right, so I think that's all I wanted to say. So let's jump back into the lecture. The last thing we did on Thursday of last week was derive this thing called the range equation, which tells you for a given launch angle and a given launch speed, how far will a projectile travel. So in this question, we have the following scenario. A soldier has a cannon that can fire projectiles at an initial speed of 2.0 10 to the 2 meters per second. The soldier wants to hit a target that's 12 kilometers away. What angle should the cannon be aimed in order to hit the target? So try to work it out. Remember, we're going to be using the range equation here and basically solving for the angle. That's what's going on in this problem. So if you don't remember the range equation, just flip back to your notes from last week. And then take a few minutes to try to work this out, see what you get, okay? Looks like you're on the right track. What does that tell me? Okay. We're looking for an angle for the sum of these every 2.9. Okay, let's take a minute to go through this one. So, can someone out there just tell me what is the range equation?
Initial velocity squared times the sine of 2 theta over g.
Yeah, so R equals V naught squared sine 2 theta over g. That's the range equation. Now in this particular problem, we're trying to solve for the angle. We know what the range is. It's a 12 meter range to hit the target, or 12 kilometer range to hit the target. So we have sine 2 theta equals R times G over V0 squared. So let's start there. Let's just say sine of 2 theta, whatever the launch angle should be to get this to work, should be the range times G over the launch speed squared. Okay, so the range is 12 kilometers. We can write that as 12 10 to the 3 meters. G is 9.8 meters per second squared. And then our initial launch speed is 2.0 10 to the 2 meters per second, and we'll square that. So without calculating theta just yet, what does this number equal? Let's crunch those numbers.
200?
You might want to check again. This comes out to 2.94. Okay? Now right away we should be able to see what the answer is, right? Because we're basically, this is saying sine of some angle equals 2.94. But is that even possible? Is there any angle where you take the sine of it and you get 2.94? Remember your trig, right? Sine only goes up to 1. That is the maximum value sine can have. So this is an equation with no solution. Sine of 2 theta can only get as big as 1. So there's no solution. What does the fact that there's no solution mean physically here?
Not about velocity.
Yeah, I mean, there's just not enough velocity, regardless of what angle we aim the cannon, to hit this target. It's just too far away. Okay? That's possible, right? The target is just too far away to hit under any circumstances. And that's what's coming out of the math here. Okay? Any questions on that? Okay, so that's our kind of warm-up problem. There's no way to hit the target under these circumstances, is the answer. So with that said, remember we derived the range equation. There's another equation that's useful that I'd like to show you. You might have even used something like this on the recent homework without knowing it. So let's see what's going on here. The maximum height of a projectile. That, of course, is just what we call the apex of the trajectory, to use more fancy language. But really just what is the highest point above the launch point that our projectile reaches? Go ahead.
I just wanted to ask a question about the range. So the range could just be like the displacement of position, right?
Yeah, so the range refers to how far you travel horizontally between launch and landing, assuming you are launched and land at the same height. Okay, that's what that is. But now we're talking about the maximum height. So there's an equation, we're going to derive this. I'll show you where it comes from. But here's how we get this equation in the first place. Okay? The idea is we're going to launch a projectile with some initial velocity, which means there's some speed we launch it at, and there's some angle at which we launch it as well. But what happens when we reach the peak of the trajectory? This is what we need to establish to see where this equation comes from. So, as you see here in red, the trajectory is shown. This is just the path that our projectile takes. It's a little parabola, okay? And remember, this is something we talked about like very early in this lecture. One of the first results we found is that at every point along the trajectory, velocity is just tangent to that trajectory. So in other words, let's take a look at the very peak of the trajectory. If the velocity is tangent to that trajectory, at the peak, it's just pointing completely horizontally. So when you reach the peak of the motion, the velocity is completely horizontal. There's no vertical component to it at all. And what that means is Vy, that's the velocity in the y direction, that's going to 0 at the peak. So this is the condition we use to say projectiles reach its peak. We say Vy is equal to 0. And then we can derive the equation that's shown on the slide from there. So let me show you how that goes. So kinematic equations. We have a lot to choose from. I'm just going to write this one down. Hopefully it looks familiar. Vy squared equals V naught y squared minus 2g y minus y naught. That's the kinematic equation I want to think about for the time being. And if we're trying to say that a projectile's reached its peak, we're going to set that final velocity in the y direction equal to 0. We just explained why that's the case, right? Initial velocity in the y direction, remember, that would be our initial speed, v naught, times sine of the launch angle. And we're squaring that. Okay? And then I have minus 2 times g. Okay, y represents a final height, final position along the y direction. So we're going to call that h. And we're going to set our initial height to 0. So this way, we can just solve for h, which is our maximum height that we reach. So to rearrange this, we have 2gh. I'm going to take this negative 2gh and add it to both sides, so now it's over here. That equals v naught squared times sine squared theta naught. So I'm just squaring this whole thing and showing how that works out. So to solve for h, all I do is divide by 2g. So we have maximum height reached is v naught squared sine of the angle squared divided by 2g. So that's a formula for the maximum height that can be useful. But it really just came from this kinematic equation and setting the final y velocity to 0. Okay? Make sense? So there's the result on the slide. That's where it came from. And if we're all good with this result and where it came from, let's practice using it, okay? So same basic scenario, we have a soldier who can fire a cannonball at 200 meters per second as the initial speed. Now let's say the soldier fires from ground level with a launch angle of 32 degrees above the horizontal, okay? So given that, what is the maximum height above the ground that this cannonball will reach in its trajectory? So just use the equation we derived, you should be able to get. Okay, take a minute or two to get that. Okay, what are we getting for this? Anybody? So I'm hearing a few different answers, but I'm hearing a lot of 570, which is good. So here, let's just do it real quick. H, maximum height, is v naught squared sine squared theta naught. By the way, this means we're taking sine of the angle and we're squaring that, as opposed to saying we're going to square the angle first. That's how you want to interpret this. So when you punch this into your calculator, do initial speed 10⁻²⁰ meters per second, square that, and then type in sine of 32 degrees and square that. That's how you want to interpret this, okay? And then divide by 2 times 9.8 meters per second squared. If you do that, you should be getting 570 meters is the height we reach, okay? Any questions? Okay, so we derived an equation. That's how it gets applied. Let's do a few more examples like this. So same scenario. We fire a cannonball with an initial speed of 200 meters per second, starting from ground level, and it flies through the air and then hits the ground somewhere else, okay? The question here is, how long is the cannonball in the air? So now you want to find a total time in the air for this cannonball, okay? Now, for this, I would advise using your kinematic equation for the y position of the cannonball. flip back to your notes, look at that kinematic equation, and see how you can apply it here. And then take a few minutes to work it out. We'll see what you get. So I would suggest using this kinematic equation right here to solve the problem. Okay, y equals y naught plus v naught yt minus a half gt squared. Try that out. Okay. Check your work. It's actually half of what we got. So might have dropped it back to 2 somewhere in there. Yeah, looks like you got it. Very nice. So for this one, it doesn't necessarily make sense to use the maximum height you found before. It's probably a more straightforward way of doing it. So here, let's go through this. A few of you got it, a few of you are pretty close to getting it as I've walked around the room, but let's just take a minute to go through it. Okay, so the idea behind this one is we launch the projectile and then it lands at the very same height that it was launched from. Okay, so it's basically traveling over completely flat ground. And that means y, our final position in the y direction, is equal to y naught. So we don't end at a different height from where we started, we end at the same height where we started. Okay? And that means y and y naught that appear in the equation just cancel each other out. So this can be simplified to say 0 equals v naught yt minus a half gt squared. Now let's take this and pull out a common factor of t from both of these terms. So this would be t times v naught y minus a half gt. See how we can factor out the t this way? And that all equals 0, of course. Okay? Now, there's two solutions here. When we're multiplying these two terms together, and we get 0, it just means one of these terms that we're multiplying together itself is equal to 0, right? That's the only way to multiply numbers and get 0. So it's either that t is equal to 0 or that this thing in the parentheses is equal to 0, which is what we're interested in, by the way. Okay, so the thing in parentheses equals 0. Now, if we take 1/2 gt with the negative sign and add it to both sides, we get v naught y equals 1/2 times gt. Okay? And that means the time, if we solve for that, is equal to 2 times v naught y divided by g. But remember, v naught y can be expressed as the initial speed times sine of the launch angle. So that's what I'll put in right there. And then we'll divide by g. So remember, this is giving me the total time it takes to travel from this initial point to this final point. That's what we want. That's the time in the air. So we have 2 times 2.0 10 to the 2 meters per second. That's our v naught. Then we'll take sine of 32 degrees, which is our launch angle. And then we'll divide that by 9.8 meters per second squared. Can someone crunch those numbers for me and tell me what the result is? Yeah, so it's about 21.6 seconds, but let's round that to 22 to keep our sig figs consistent. Okay, so this projectile spends 22 seconds in the air before it hits the ground. Do we have any questions on how that works? Okay. By the way, for projectiles, if you know the starting and the ending heights, usually to find the time in the air, you're going to be using this formula. Okay? You can see how it naturally falls out, that the time is something you can solve for. All right, so we're going to do one more example with projectile motion, and then we're going to move on to a new topic. It's actually the last topic we're going to cover that appears on the upcoming test, which is relative motion. This last topic is kind of tricky, so I want to spend almost an hour on it today, and then the full time we have on Thursday, because again, it's a sort of tricky topic. But before we get there, let's do one more example of projectile motion, which is firing a projectile over a slope. So let's say you're at the top of the mountain shown here, which slopes up at 35 degrees relative to the horizontal. So let's say from the top of the mountain, you throw a pebble horizontally with an initial speed of 25 meters per second. We want to answer two questions about this. First, how long is the pebble in the air from the moment you throw it until the moment it hits the ground? And then how far down the slope does it travel? So this distance shown here. Now, normally, when we've been dealing with projectile motion problems, we've been kind of choosing the algebraic approach, where we just write down an x equation and a y equation separately for the motion. Now, we could do that here, but I'm going to show you a different way to solve this problem, which is the graphical approach. It's just simpler, cleaner as a solution for this type of problem. So let's just see how that works, okay? So, here's what we're going to do. I'm going to write down a kinematic equation that you've seen before, but I'm going to write it in vector form. So this says initial position R, final position R equals initial position R naught plus initial velocity V naught times time plus 1/2 AT squared, where A is our acceleration vector. So we've seen this before, right? Let's just slightly rewrite this. Let's subtract initial position R naught from both sides. So now what we have is R minus R naught equals everything else that's here, which is V naught T plus 1/2 AT squared. So when I take R minus R naught, that's final position minus initial position, what do we call that?
Displacement?
That's what we call displacement, which is given by delta r. Okay, so this is an equation for the displacement of the pebble as it goes down the slope, basically. Okay? So let's see. Let's just start with the basic picture of what's going on. We have this 35-degree slope. We throw a pebble down the slope like this, and then it lands somewhere on the slope, right? Okay, so my v0 vector, my initial velocity vector, which direction is that pointing in? Remember, we throw this pebble just completely horizontally. So my v0 vector is going to be completely horizontal, and it's just going to be multiplied by some time, okay? So what I'm showing you is v0 t as a vector on a diagram. Okay, does that make sense? My initial velocity is horizontal. What direction is my acceleration? It's down, right? It's a projectile. It's moving under the influence of gravity alone, which means its acceleration is straight down. So this could be my 1/2 at squared vector. And you see, in the equation I wrote down, I'm quite literally adding these vectors together. So in the diagram, I'm just showing you what that looks like when the vectors are added to tail, okay? This is just a diagram of what the equation is saying, okay? Okay, then, the resultant vector we get is delta r. The displacement, the overall displacement as the pebble goes from the top of the slope to where it lands. So just to be clear, this would be the starting point of the motion of the pebble, and then this would be the ending point, right? And then I'm just going to mark off an angle right here. This is the same angle as the mountain slopes up at, right? So if we call this, I don't know, alpha, alpha is the same as the 35-degree angle that we've seen before, okay? Because again, this just goes straight from the point on the slope where we start to the point on the slope where we end up, and the slope goes down at a 35-degree angle. So we know what that angle is, okay? Does that make sense how I got that in the diagram? Okay, so I'm actually going to use just this picture where we have a nice right triangle to solve for both of the variables, okay? Okay, so we have a little bit of freedom. We can just write down any kind of equation that relates the different sides here using what we know about trig. But what I'm going to suggest is let's start by using the tangent function, okay? Okay, so if I take tangent of some angle, what is the definition of tangent? In terms of opposite, hypotenuse. So tangent is not that, it's opposite over adjacent, okay? And remember, we have a right triangle, so it's totally cool to use the tangent function, which applies to right triangles, okay? What's the opposite side from my angle alpha in this diagram?
Acceleration.
Yeah, it's this 1/2 at squared, but let's think of it as the magnitude, because I just am caring about the length of this side, right? And then what's my adjacent side in the diagram? What's the adjacent side to the angle? It's the v0 t, okay? But again, if I'm thinking of this as a length in a triangle, then we're referring specifically to the magnitude, okay? So, in the case of a projectile, our acceleration, the magnitude of it is just g, okay? So I've been referring to some generic acceleration here, but we know it's a projectile, so it's just g that we're talking about, right? For acceleration. So this would be 1/2 gt squared, and then this would be v0 t. So we have tangent alpha equals, let's simplify this a bit. I have a factor of t that I can cancel on the top and bottom, right? So I'm just going to have gt divided by 2 times v naught when I simplify this expression right here. And again, I'm trying to solve for the time. I want to know how long it takes from throwing the pebble until it lands on the slope. Solving for t here is going to get me that. So here's what I have. I have 2v naught times tangent alpha divided by g. That gives me t in this expression, okay? And at this point, I can just start plugging in some numbers. So what do we have? We have t equals 2. V naught is how hard we throw the pebble initially, which is 25 meters per second. And then I'll take tangent of alpha, which is the angle of my slope, which is 35 degrees. And then I'll divide by g, which is 9.8 meters per second squared. And that will give me the time that I want. Can someone crunch those numbers for me? Yeah, so it takes 3.57 seconds until we land on the slope, or about 3.6 seconds to the proper number of sig figs, okay? So again, this is kind of a novel approach compared to what we've been doing, but it offers a more like clean solution or a quicker solution. Okay, so that's how long it takes. The other thing we want to know is how far down the slope have we traveled, okay? So if our displacement vector delta r is shown here, the length of that displacement vector, starting at our initial point, ending at our final point, that's going to be the distance we want. That's going to be how far down the slope we've traveled. So let's just try to think of some equation that could bring that into play somehow. And there's more than one way to do this, but I'm going to suggest trying this out. Let's just bring in another familiar trig function. Let's try cosine. And again, in reference to this triangle that we constructed. Now, what is the definition of cosine, just in terms of our sides, opposite, adjacent, and so on? How does cosine work? That's adjacent over hypotenuse, right? Okay, what's the adjacent side? That's v naught t. We're thinking of it as a length, so that's just the magnitude of that vector, right? And then what's our hypotenuse? The long side. What's the hypotenuse here? Yeah, it's the magnitude of delta r. Okay, so I'm trying to solve for the magnitude of delta r. So let's multiply through on both sides, put it over here, and divide by cosine alpha, which puts it down here. And that gives us delta r is v naught t over cosine alpha, okay? So we now know the time that's relevant here, so we can actually solve for this. So for v naught, again, we have 25 meters per second. For the time, we have 3.57 seconds. And then we'll divide that by cosine of alpha, which again is 35 degrees. Can someone tell me what this works out to? Yeah, 109-ish, but we'll round that to 2 sig figs, 110. So it takes 3.6 seconds in the air to land, and then when it does land, it's 110 meters down the slope from where it started, okay? Now again, this is just the graphical solution. You could also write x equals x naught plus v naught xt, and y equals y naught plus v naught yt minus a half gt squared, and so on. You could do it this way. It's just a little bit trickier. Okay, so we don't have time to show the solution, but while we're working on problems in lab this week, if you want to see how it works this way, I can show you. Okay? Any other questions? Okay, so that's pretty much all we're going to talk about for projectile motion. So we're going to move on to a new topic, which, as I mentioned, is the last topic that's going to appear on the test, and it's relative velocities. Now, just a little bit of caution. This topic, if you really understand the concept, the math isn't too bad, but conceptually, it's pretty tricky. Probably the trickiest concept we've come across so far, just in terms of conceptual difficulty, okay? So we're going to spend basically the rest of the week on this. Hopefully it'll start to click. So I'm going to start with this question, which is really just meant to test your intuition. You shouldn't write down anything. You should just be able to tell me off the top of your head what the answer is. And then we'll see, why is your intuition correct. All right, so here's what's going on. Alice and Bob are on one of these moving walkways that you find at airports typically. And the moving walkway itself has a speed of 1 meter per second. So that's just the belt moving across the ground, how fast it's moving. So Claire is standing still on the ground. She's not on the walkway. Alice is standing still, but she is on the walkway. All right? Okay, then we have Bob, who is on the walkway, and he's actually walking. Okay? So Alice, she looks ahead at Bob, and she measures his speed to be 1 meter per second. Okay? So what would Claire say that Bob's speed is? If Claire were to measure Bob's velocity, what would she measure in this case? So think about it, but it should be pretty, straightforward, right? What's the answer?
B.
So who thinks it's A? B? Everyone. Okay. Good. So what did you just do there? What did you do in your head to get to the number 2?
I add Alice speed plus Bob's speed.
Okay, good. That's the right intuition. We just want to add these two speeds together to get some kind of combined speed, right? That's pretty straightforward. Where this becomes less straightforward is where things are not moving just in one dimension like this, but instead they're moving in 2 dimensions. So let me give you an example of that. Let's say I'm trying to cross a river, right? Maybe the river's flowing this way and I want to just row my boat across. That's now a 2-dimensional problem where I have to sort of add the velocity of my boat to the velocity of the river. Another example would be flying a plane into the wind, right? You have to add the wind velocity to the plane's velocity in some way. That's where it gets a little trickier, okay? But the basic idea of addition is going to apply. It's just going to be with vectors, okay? And, one thing you should take away from that example is that velocity itself is relative, okay? It actually is a meaningless statement for me to say, I'm going at 2 meters per second, right? Unless I say relative to what? Okay, because of course, different observers, like we saw in the previous example, they can look at the same object and measure different velocities for it, right? The person on the walkway says Bob is moving at 1 meter per second. The person standing on the ground says 2 meters per second. Neither one of those is the right answer. It's just a relative question, okay? From the standpoint of physics, there's no correct way to view velocity. It's just relative to who's observing it. So let me just give you another example of this kind of thing. So we have 2 cars driving down the road, a red car and a blue car. And they're both going 60 miles per hour. But when we say 60 miles per hour, implicitly we mean relative to the road, okay? That's what that means. So there's someone standing on the side of the road observing both of these cars go by. So of course this person standing on the side of the road is going to say the red car is moving at 60 miles per hour, right? Literally, if she had speed gun, she would register that with her speed gun, right? But the blue car would say, the red car is standing still, right? Because the distance between the blue car and the red car is not even changing at all, is it? The blue car and the red car maintain the same distance from each other. And quite literally, if this person took a speed gun and took it and pointed it at the red car, it would register 0. So relative to the blue car, the red car has 0 velocity. So the point is, again, this is just another example of how velocity is relative. And if you want to say something specific about velocity, an object is moving this fast in this direction, what you need is something called a frame of reference. And we didn't really explicitly say this yet, but you need a frame of reference. Okay, so let's now talk about what a frame of reference really is and how it comes into play. Okay. So here's what a frame of reference is. A frame of reference is just a coordinate system. It's a coordinate system that you set up and you use to measure motion. And when we say an object has a certain velocity or a certain acceleration or a certain position, it's just relative to that coordinate system that you've set up. But the thing to realize is there's no one special coordinate system to use that is preferred from the standpoint of physics. You have a choice. Okay? And one frame of reference can be moving with respect to another. And when that's the case, we have a conflict as far as what we're measuring. Okay? So why have I never talked about this? Because so far, up until this point, we've always been assuming that our frame of reference is just fixed to the Earth. So quite literally, just imagine a set of coordinates that is just planted to the ground. Imagine a y-axis that just goes up like this, and an x-axis that goes horizontally like this, and that set of axes is just planted to the ground. That's what we call the ground frame of reference. Usually, if we don't say otherwise, we're talking about the ground frame of reference when we measure things. Like all of the projectile motion problems that you've seen so far. We're using the ground frame of reference, right? But you don't have to do that. So here's an example. We have a person standing still on the ground. So the set of coordinates, that's basically not moving with respect to this observer, is the ground frame. Now we have a truck. Let's say the truck is driving to the right. We can imagine a set of coordinates that's not fixed to the ground, but it's actually moving with the truck. So let me just show you an animation of what that looks like, okay? So when we talk about the truck's frame of reference, we're measuring things with respect to these coordinates that are actually moving along with the truck. Does that make sense? So this person, who's in the back of the truck, has 0 velocity with respect to these truck coordinates, right? Although he wouldn't have 0 velocity with respect to these ground coordinates, okay? And there's no right answer. Both of these perspectives work just fine. You have to just be clear about which one you're using, because they will trip you up if you don't. Do we have any questions about this idea? Okay. So, yeah, that has to go again. So this is taking us to a really important equation, which is the relative velocity equation. So I will show you where this comes from. We'll derive it. But let's first talk about what this equation is saying. The relative velocity equation, it's also known as Galileo's equation, because a scientist from the 1600s, Galileo, actually discovered this. He didn't write it exactly in this way, but he pretty much figured this idea out. It relates the velocity of an object as seen in 2 different frames of reference. Okay, so in this equation, we have 2 frames of reference. We're going to call them A and B. Okay, so whenever you see the A subscript in the equation, we're talking about frame of reference A. You see the B subscript, we're talking about frame of reference B. And those can literally be anything. We'll fill in different things for A and B in actual examples, but this is just what the equation looks like generically, okay? Now, there's a kind of notation that's being used here, and I want to make sure you understand the notation. So let's take a look at the first term just as an example. This says VOA. So O is just going to represent some kind of object that we're keeping track of. It can be anything you want. It can be an airplane, a boat, person walking around, whatever. It's just some kind of object. And when we say VOA, that means we're measuring its velocity with respect to frame of reference A. If you see VOB, that means we're measuring the object's velocity relative to frame of reference B. And of course, these are two different things, right? Then finally, this term says VBA. What does that mean? Well, it's the velocity of frame of reference B with respect to frame of reference A. So again, think about the animation of the truck moving before, right? The truck frame of reference itself was moving with respect to the ground. That's what this third term is allowing for, okay? So here's the picture you should have in your mind. We have frame of reference A, we have frame of reference B. These are just two different sets of coordinates that we use to measure motion. And then we have some object moving around. And again, the exact velocity that we would attribute to this object depends on which frame we're going to use to measure it. Now at the same time, imagine that the frames of reference themselves are moving with respect to each other. So let's say in this picture, we have frame of reference B moving in this direction with respect to frame of reference A. This puts together all of those different velocities in one neat equation. Okay, so I think I've explained what this is basically saying, or the ingredients that go into it. So let me show you a derivation of this, so hopefully it becomes clear. All right. So we're going to set things up like this, okay? I have a set of coordinates right here, which I'm going to call frame A. And then I just have some other set of coordinates here, which I'm calling frame B. So notice how there are different frames of reference, but I'm aligning the axes in the same way, right? So like X is to the right, Y is up, axes are aligned. Okay, now let's just put an object on the page somewhere. Let's say this is our object. Okay? So the position of our object, as we would measure it in the frame of reference B, is this right here. So if I go from the origin of frame of reference B out to where the object is, that would be the position of the object measured in frame of reference B. So I'd write that as ROB. That's how the notation works that we've just set up. Okay, ROB means position of our object in frame B. Okay, if I take a vector that goes from the origin of frame A all the way out to the object, that would be ROA. It's the position of our object as measured in frame A. Okay? And then finally, if I draw a vector that starts from the origin of frame A, and then it ends at the origin of frame B, like this, well, I could call that RBA, because it's the position of frame B as measured from frame A. So hopefully you see what these vectors kind of mean. And hopefully you see that we have a vector addition going on in this diagram. Can you tell me what that vector addition is? I have two vectors tip to tail, right? This one and this one giving me this resultant vector right here. So let me just write that down. It's ROA equals ROB plus RBA. So if I want the position measured in frame A, I would add these two together and get that position out, okay? Now the last thing we're going to do here is actually pretty simple. On both sides of the equation, I just want to take a derivative, or think of this as a rate of change, okay? If I take the derivative of what's on both sides, I'm going to have the derivative of this r equals the derivative of this r plus the derivative of that r. But what does it give us when we take the derivative of a position, generally speaking? That's a velocity, right? So if I just take the derivative on both sides, I'll get VOA equals VOB plus VBA. And that's the result that I wanted to show you. So if I know the velocity in one frame of reference, I can get it as seen in the other frame of reference just by applying this equation. Okay, that's what it does for you. It takes you from one frame of reference to another. Okay, any questions on this? I'm sure there's some questions, but hopefully examples will answer these. Okay, now let's talk a little bit about how to set this equation up, because this is where things can go wrong. How do I know that I've set this up properly? Okay, so what I'm about to tell you is not super deep or anything, it's just a trick, and it works to make sure you set it up properly, okay? So we have a whole bunch of subscripts floating around, right? O, that represents the object. A and B represent two frames of reference. So how do I know that when I write down the equation, it's in the right form? So notice something here, okay? The subscripts on the outside, okay, that would be O and A, they appear in the exact same way on both sides of the equation, right? Because my outside subscripts over here are O and A, and then over here, they're O and A. Okay, so they just match in that sense on the left and right side. And then my inside subscripts, they have to match too. So I have B and B right here. And that inside subscript that appears on this side of the equation, it doesn't appear at all on that side of the equation. Okay, so whatever your situation is, whatever subscripts you want to use, as long as it kind of fits this general format, you know you've written down the equation properly. Okay? So does that make sense what I just said? It's just a little trick to make sure you set it up properly. Okay. So of course, the first example I showed you with this moving walkway, you don't need all this fancy math to really do it. It's pretty intuitive. But again, I want to show you how the equation we just derived applies to this situation, because once we get to more complex examples, there's no way around using the equation, okay? So here's the notation we'll use, okay? We have A, B, and C. A is going to be Alice's frame of reference, and of course, that's going to be moving along with the walkway. B, that's the object in question that we're interested in, keeping track of. Well, he's a person, not an object, but you get what I'm saying, right? And then Claire is another frame of reference, right? This would be everything measured from her perspective. That would be fixed to the ground, okay? So let's just see how we write the relative velocity equation in this case. Remember, we want to know what Claire sees, what she measures as Bob's velocity. So that would be VBC. This is the velocity of Bob relative to Claire. That's what we want to know. How do we get it? Well, let's set up our equation and just make sure it has the right format. So B and C should be my outside subscripts like this, and then A should be my inside subscript like this. So as long as that's the case, I know I've written it properly. So we have VBC equals VBA plus VAC. Let's just say this in words real quick. The velocity of Bob relative to Claire equals the velocity of Bob relative to Alice plus the velocity of Alice relative to Claire. And of course, what goes in each one of those is just 1 meter per second I hat, assuming we're taking the right to be the positive x direction. Because of course, the velocity of Bob relative to Alice, 1 meter per second in the positive x direction. Velocity of Alice relative to Claire, 1 meter per second in the positive x direction. That's why you add these together and get 2, okay? So do we all see how to set this equation up in this particular example? All right, let me ask you this. What if Bob is walking against the walkway at the same speed? What does Claire measure in that case? So let's say Bob is walking at 1 meter per second against the motion of the walkway.
Nothing.
0, right? Because basically, now this would be -1, and you would get 0 out. In that case, you have a treadmill, right? That's just what a treadmill is doing, right? Okay. Let me show you another example from the show Mythbusters. You may have seen this. Does anyone watch this show still, Mythbusters? No one? No one watches Mythbusters? Okay. So here's what's going to go on. So there is a truck that has a cannon, which is going to fire a cannonball out the back. So it's going to fire the cannonball opposite to its direction of motion, okay? And it's going to try to match exactly the speed of the truck, the speed that it fires this cannonball, okay? So what are we going to see from the perspective of just an observer on the ground for this cannonball?
It's going to stay in the same position it was dropped?
Yeah, we're gonna just see it kind of drop straight down. Even though it's being fired out the back at a pretty high speed relative to the truck, relative to the ground, it doesn't have any initial speed.
I have a feeling that we are very close to a perfect demonstration. We're going to see that ball drop.
With the forward and backward momentum matched as close as they're going to get it, the pressure's on Grant for a perfect release.
I don't know about you guys, but that looked pretty good to me. Let's check the high speed.
It really looks good to the naked eye, but the judge in this case is the high speed.
There, see that?
It's in the air. It's not. It just falls.
Look at that. I mean, look, it doesn't move at all. It's going straight down.
All right. So I think that's a pretty cool example because the velocity of this ball relative to the truck is exactly the opposite of the truck's velocity relative to the ground. So when you add those two together in the relative velocity equation, they just exactly cancel out to give you 0. That's what's going on here. Any questions on this one? You can check the link here if you want to see the full video.
I have a feeling that we are
Oh wait, let's get out of that. Okay, so here's one for you. We have a river which is flowing from west to east. So it's flowing this way, west to east, at a speed of 1 meter per second. Of course, when we say that, we're measuring that relative to the shore, right? Let's say that you're capable of rowing your boat at a speed of 1 meter per second. And what that means is relative to the water, you can row your boat at 1 meter per second. So let's say that you start here at the south shore. And you just point your boat due north and start rowing at full speed. The question is, what will your velocity with respect to the shore end up being in this case? So we're going to give this velocity that you come up with in xy form. So our coordinates that we'll use to do this are right here. Positive x direction is going to be east. Positive y direction is going to be north. So relative to the shore, what will your velocity look like? So try to work it out. And again, even if you kind of intuitively know what the answer should be, get some practice writing the relative velocity equation out with all those subscripts to get the answer, okay? It's important to be able to do that. So try it out, see what you get. you see how to write it out with all those subscripts. That's probably harder than actually just getting the answer in this case. So see, we try like R for river, S for shore, V for boat, something like that. Definitely have the answer. We try to see how to construct the equation symbolically with the subscript. Looks like you're getting it. Okay, so I see some people are getting this. Anyone want to shout out the answer? Say it again? C? Yeah. It should be this. Now let's try to get an intuition for what's going on here. Of course, if there were no currents in the river, and I just pointed my boat due north and started rowing, well, of course, relative to the shore, I would see the boat moving due north. But the thing is, the river is also carrying me downstream as I do that. So overall, my motion is going to be something like this into the first quadrant, which is why we can pretty much automatically say it's answer C. But again, I want you to get some practice writing down this equation, because as the examples get more complex, there's really no way around it. You're going to have to use this and just be kind of systematic in how you set things up. So here's what we'll do. Subscript notation. B is our boat. That's our object of interest. I'll use a capital R for the river frame of reference. So to be clear what this means, imagine a set of coordinates that's moving with the river itself. So imagine like a raft just floating down the river, moving with the currents of the river. That's the frame of reference we're talking about. Let's use S for frame of reference fixed to the shore. So you could also call this the ground frame of reference, right? Okay, so what velocity am I interested in knowing? Velocity of the boat relative to what? What am I interested in knowing? I want to know what it is relative to the shore. I want to know VBS, okay? So what do I do? Well, I know that this is the sum of two different velocities, and I just need to know how to set up the subscripts for those two velocities I'm adding. Well, the outside subscripts should match, so I should have a B here and an S here, and then my inside subscripts should cancel out, okay? So VBS equals VBR plus VRS. Does that make sense? Okay? VBR, that's the velocity of my boat relative to the river. Well, relative to the river, I'm just moving due north at 1 meter per second. So that's the y direction. So I'd write 1 meter per second j hat for this first vector. Okay? VRS, that's the velocity of the river relative to the shore. So that's just the velocity of the currents in the river, which is 1 meter per second due east. Due east is the x direction, so this is 1 meter per second I hat. So that's where this answer comes from, okay? Do you have a question back here? Okay, just checking. Are we clear on how this works? So again, relatively straightforward examples so far. Just want to make sure we know how to use this equation, and then we'll build up the complexity as we go. So here's another one for you. It's a follow-up. Okay, so we have the same river. It's flowing from west to east like this at a speed of 1 meter per second. Now, let's suppose you can row a little bit better than before. Let's say the speed at which you can row your boat relative to the water is now 4 meters per second. So the goal here is something a little different. We want to know in what direction should you aim your boat so that you travel due north across the river without being carried upstream or downstream. Okay, see in the previous example, if we row in the way described, we're going to move downstream. We don't want to do that. We want to just move straight across relative to the shore. Okay, we want our velocity relative to the shore to just be due north. So, roughly speaking, what do we have to do to accomplish this? How should we point the boat, in other words?
Traveling the opposite direction of the river?
Okay, so not the exact opposite direction, of course. I know that's not what you meant, but I just want to point something out, right? If I go exactly into the current like this, then I'm just going to be traveling upstream, right? If I point my boat like this, I know I'm going to be carried downstream. It looks like I should point my boat at some kind of angle in this direction. I have to kind of fight the current a little bit, but not too much that I start going upstream, right? So there's some kind of perfect angle that works out here, and we're going to figure out what that is, okay? So let's do this. So for this, I think it's best to use a graphical sort of approach, okay? So we're going to start with the same exact relative velocity equation as before. VBS, that's the velocity of the boat relative to the shore, equals VBR. That's the velocity of the boat relative to the river, plus VRS. That's the velocity of the river relative to the shore. So that's the equation we have, same as before. But now, I want to look at each one of these vectors and just kind of get a sense of which way it's pointing, okay? So this one right here. What should the direction be for the velocity of the boat relative to the shore? What do we want it to be in this case?
North.
We want this one to be due north, right? That's what it means to not be carried upstream or downstream. It means relative to the shore, you're just moving due north, you're not moving east or west, okay? What about this guy, VRS? What direction is that pointing in? That's due east, right? And then this one, I don't know what direction it's pointing in. That's what I'm trying to find out, right? That's going to tell me how to angle my boat to fight the current just the right way that I go straight across. So I'm going to add this vector to something that's pointing due east, and then I'm going to get something that's pointing due north. Can you see what this sort of looks like? This vector is going to be pointing into the second quadrant somewhat like this. Okay? My second vector is pointing due east. So that's what it looks like when I add these two together, right? So this is VBR, and this is VRS. Okay? And the resultant vector I get is this one. VBS. All right, so do we understand how that's the vector diagram? Okay? Now here's an angle I can find right there. I'll just call it alpha. I do not know what that angle alpha is, but if I did know what it was, that would tell me what direction to point my boat in to accomplish this, right? So again, I could, if I wanted to, do this algebraically, where I write a separate x and y equation, but I think in this case it's just way simpler to use this diagram because we have a nice right triangle and the math will be really simple, okay? So, all right, one thing we could try is just writing down some trig functions, okay? Let's try writing sine of alpha as a starting point. Now again, remind me, what is the definition of sine? It's the opposite side over the hypotenuse, right? Okay, in this case, what is the opposite side? Yeah, in particular, if we're thinking of this as a length on a triangle, it's the magnitude of the vector VRS. And then what's my hypotenuse? VBR, okay? Magnitude of that vector. Now, without getting kind of lost in the symbols, what number do we assign to the one on top? What is the speed of the river relative to the shore? That's the 1 meter per second, right? And what's the speed of our boat relative to the river? That's how fast we're capable of rowing, right? What's that?
4 meters per second.
So it looks like to me, that's just 1 over 4. So if I want to find out what alpha is, I'm taking the inverse sine of 1 over 4, right? And what does that give me? Inverse sine of 1 over 4. Yeah, so it's 14.5 degrees. And let's be clear, this is not the standard way to measure an angle. So we could call this, if we think about it, west of north. Okay, because we're starting north like this, and if we had 14.5 degrees west from there, we get to this vector. So I'll write this as 14.5 degrees west of north. Does that make sense? And of course, if I were to change the numbers around, you get different angles, right? But any questions on how we set this up? Okay. So let's keep going. Just one last kind of conceptual thing I want to show you before we end this one. It has to do with a sort of symmetry in the equations, okay? The best way to show you why this works is to show you an animation. Hopefully it's just crystal clear once you see the animation, okay? So I want you to think of these two different frames of reference we have. So we have let's say we have a river, it's flowing due east, so it's going to the right at 10 meters per second from our perspective. Now, frame of reference B, that's going to be the frame of reference you see here that's moving with the river. So imagine there's just someone standing on a raft that's just floating, moving with the currents in the river. That would be frame of reference B, okay? Frame of reference A, that's the perspective of someone just standing on the ground on the shore, okay? Those are the two frames of reference. Okay, so that's all we have so far, just two frames of reference. So this is what the situation looks like from the perspective of frame of reference A. What do we see? We see frame of reference B moving past us in the positive x direction at 10 meters per second. So let's just write that using our notation. This says VBA, that's the velocity of B relative to A, is positive 10 meters per second I hat. Okay, pretty straightforward so far. Let's just flip the perspectives now. Okay, let's try to imagine what does it look like from the perspective of the person on the raft.
Trees moving in the opposite direction?
Yeah, if you're the person standing on the raft, you're seeing the trees and person A moving to the left past you, right? This is what it looks like from the other perspective, okay? Pretty straightforward, right? So, in other words, if we were going to flip the subscripts around to say VAB, that's velocity of A relative to B, well now we're moving in the negative x direction, right? So negative 10 meters per second I hat. Now that's just an example of something more general, okay? If you have a relative velocity and you want to flip the subscripts around, which is just a matter of flipping the two perspectives around actually, you just introduce a negative sign, okay? And sometimes this is something you want to do in the relative velocity equation. All right, so let me just give you one more example of this, right? I'm driving down the road, let's say I'm driving north, that's 60 miles per hour. That means my velocity relative to the road is 60 miles per hour going due north, right? But if you were to ask, what is the velocity of the road relative to me? I see the road going by me due south, right? At the same speed. Again, another illustration of this kind of symmetry. So we all get this? We're going to use this idea later on. But that's all for today. More examples on Thursday.